Hello everybody, how are you? This is lesson 3A. It's about linear functions. So there's a lot of basic stuff here. There's this particular lesson's got a combination of theory. We're going to talk some basic theory. It's fairly simple, but then also we're going to talk about some practical stuff, algebra stuff. So it's not it's not too complicated, but it's important. So we're talking about linear functions. So today's goal, you need to be able to recognize when something's a linear function. You need to be able to recognize the dependent and independent variable. And I guess by this, it means know what we mean by dependent and independent variable. You need to be able to recognize the slope and intercept of a given linear function, which these are two numbers, by the way. You need to be able to calculate the slope and intercept and form of a line going through two given points. So somebody will say, here are 2 points. Tell me the equation of the line that goes through them. And you'll be able to find the x and y intercept of a given linear equation. So let's begin. I want to talk about a little transition we're about to make in this course. We were talking about graphing a function. So somebody gives us a function. Call it f of x, and we draw a graph of it. How do we represent that procedure algebraically? What we did was we say, okay, y is equal to f of x is the graph. What did that mean? That means you start with a value of x. And then you take that number and you plug it into the expression, and you get out a number, which we call y. And these two numbers, this one and this one, are then put in as the coordinates of a particular point on the graph. Right? So x is your input and y is the output. Okay, of the graph. So graphing was fun in this. However, graphing is such a common procedure when it comes to the mathematics of functions that a shorthand has developed, and it's a little bit less explicit than the one we're used to talking about. How can I say this? Essentially, sometimes you see people phase out, especially in the topics we're talking about today, linear functions. They phase out the idea of function notation. So before, up until now, we would say, here is a function. It's an algebraic expression. It's a function. It has a name. Its name is f. It has a variable. Its variable is x. If I wanted to graph that function, I would say, hey, set y to equal x squared plus 2 and use that to graph. So the first expression is a function, and the second expression is a graph. Okay. So the way we do it in the big leagues is often we don't start with this step. Instead, we just start with this step. So somebody might then tell me, okay, y is equal to x squared plus 3x minus 2, and they'll say this is a function. And it is. It really is. In some very roundabout way. It's not implicit about it. What this often means is, you can draw a graph using this recipe. And then you can use the graph like a function. So you could say, oh, when x is equal to 4, what's the value of y? What's the output? And we've covered kind of all that already. But the long and the short of it is that we treat the x in this expression like the input, and then the value of y is the output of the function. So if someone will say, evaluate this function at x equals 2, we don't have function notation anymore. You just say x is equal to 2, and then you go y is equal, and you plug in the value 2, just like you would with function notation. So that's equal to 4 plus 6 minus 1. So that's equal to... Oh, wait, hold on. I copied this down wrong. It's supposed to be 2. And this is equal to 8. So the value of x is the input. The value of y is the output. Does that kind of make sense? I don't want to overcomplicate things. It's just that with polynomials, often we don't start by defining what the function is and then talk about its graph. We just say, here's an equation. Y is equal to blah, blah, blah. You just don't stop. You just give and say, x squared plus 3x minus 2, and you just go from there. They say, this here is the function. But before we go too much further with that, there's actually a really good reason for having done it, and it has to do with science and science analysis. So in science analysis, what'll happen is you'll be doing an experiment, right? So here you are doing an experiment on, I don't know, a plant, okay? And what you'll do is there's going to be some aspect of the experiment. Experiments usually involve systems where there are lots of potential different ways for things to change. You keep everything the same, and then you have something called a controlled variable. Like you might say, okay, what I'm going to do is I'm going to have a whole bunch of different plants. They're all clones of each other. I'm going to give this one 1 drop of water, this one 2 drops of water, this one 3 drops of water, this one 4 drops of water, and we'll see how they're doing the next day. So what you do is you control one aspect of it, and then after that you measure the outcome. Okay? And so there's two kind of numbers in these experiments. The first number is the one you're controlling, the only one that you're changing. All the rest you're holding fixed. You're changing this one variable. And the second is the one that you're measuring. Okay? So this is related to why we write out expressions like this without stopping with an intermediate bit. Essentially, this expression is an equation of two variables. There's the variable x and the variable y. And I mean the variables, they're there to represent you know, a number, but I don't know its value, or maybe its value hasn't been fixed. Okay? X in this case is the input, y is the output, as we just discussed, if we think about this as a function. But then, if you think about this in terms of like doing a science experiment, x is the one you have control over, and y is the one that you're measuring. So we call x the independent variable, and we call y the dependent variable, which just means that the value of x can be anything we want, and the value of y depends on the value of x. And so if we think about it in that way, x is the thing we're controlling, y is the thing we're measuring. We're trying to figure out how y depends on the value of x in our experiment. And dividing things up this way is it's actually a pretty functional way. Ooh, that's a pun. It's a pretty useful way to relate essentially all of us discussing functions with, you know, doing experiments in science, right? So you might be like, hey, I did an experiment on the x-axis. These are the drops of foods. I gave a plant. This height is the height after 3 days. And, you know, you're like, oh, look, this plant, sometimes you got a big, and then more food, you kind of kill it off. And what this graph represents, well, it represents the data. Definitely represents the data. But another way to think about this graph is it represents the relationship between the drops in food and your measured height after 3 days. In other words, it is input, output, a function. Okay? So the long and the short of it is that we often present functions not in terms of function notation, but you'll often present a function as the relationship between two sets of variables in an equation. So this is an equation relating the value of the dependent variable to the value of the independent variable. And that's how we represent functions. It's pretty fun. Okay. And this is super relevant because often when we talk about linear functions, which is the topic of this lesson, we aren't given a linear function as just a polynomial. Instead, you'll be given a linear function as an expression like that. So let's begin. Degree. All right, let's hold on. Erase. Okay. So at the very start of us discussing polynomials, I mentioned that polynomials are sorted according to their degree, and that different polynomials will behave in characteristic ways according to their degree. That's why they're sorted in that way. So degree 0 polynomials are constant numbers. They don't behave in any way because their value is constant. So we're not even going to talk about degree 0 polynomials. Degree 1 polynomials are called linear polynomials. Polynomial functions are called linear functions. The reason they're called linear is because if we draw their graph, you get a straight line, a straight flat line. Sometimes it's horizontal, sometimes it's tilted, but you get a straight line. We are going to get to that in a later lesson. You know, soon. I think the next one we get to graphing. But before then, we need to talk about the general form. So, as I mentioned before, our traditional way of representing linear polynomial might be like that. There, you got a nice linear polynomial function. The standard way that linear polynomial functions are represented to students isn't like that. Instead, they will be written y is equal to 3x plus 2. As I said before, this is implicitly a function where x is the input, dependent, and y is the x is the independent and y is the dependent variable. Okay? So, if somebody's talking about a linear polynomial or a linear function, they might give you an expression like that. Now, how do you tell linear polynomials, how do you tell linear functions apart? Well, it's not as easy as it might look. Consider the following examples. Okay. All of these are the same linear function. What? Look at that. What? Linear function? What? Linear function? Huh? Okay. So they are. But how do we even start talking about that? There's a method. The method for examining a linear function involves essentially putting it into a standard form, so rearranging it in a way that you can get a good look at it. I don't know if there's a good way to talk about it. You think about like mugshots, right? Hey, the cops want to know if some criminal is a particular criminal. So every time they catch someone, they bring them into the office and take a photograph of them. but they need to turn them in a specific standard way so that every time they're looking at them after that, they're looking at them from the same direction. We're essentially doing the same thing. We're rearranging it so it has a standard shape that we can use to compare it to all of its neighbors. So the method's like this. Step 1, the isolate variable y. By isolate variable y, we mean rearrange the equation using algebraic laws so that y is all alone on one side. 2, expand it completely. And 3, compare the coefficients. This is our method for comparing and analyzing linear functions. So let's just start. Isolate the variable y. I'll start with the top one. A variable y is on the left-hand side, but there's that x squared with it. So I'm going to subtract x squared from both sides. Okay. Expand completely. It's already completely expanded. All right, compare their coefficients. There's a 3 and a 2. Compare it to what is a good question. All right, let's try the next one. Isolate variable y. Right now, y is alone. There's nothing being added or subtracted to it, but it's being multiplied by 2. So I'm going to divide both sides by 2. 6x plus 4. And now I'm going to expand. 3x plus 2. And compare the coefficients. Look, these coefficients are the same as these coefficients. A1 is equal to 3. A0 is equal to 2. Yeah, just like we said when we were talking about polynomials way back when. All right, y has already been isolated in this example, but I still need to expand it. 3x plus 3 minus 1 is equal to 3x plus 2. Compare the coefficients. The 3's there, the 2's there. It's the same expression. What about this last one? Wow, y is super all tied up in other things. I'm going to start by multiplying both sides by 3. Now I'm going to subtract 1 from both sides to isolate y. 3x plus 1 minus 1. And now I'm going to expand it. 3x plus 3 minus 1, 3x plus 2. Okay, it's the same. It's the same in every case. So even though these expressions don't look linear and they don't look like the same expression, they all represent the same function when I expand things out. Okay? This particular form of a linear function where y, oh no, where y is all alone on the left-hand side, and x, all the things on the right-hand side look like that. This has a name. This is called Slopeintercept form. Which looks like this. Y is all alone on one side. There's a number in front of the x, and then added to a constant. Okay. Why aren't we going A1, A0? We're not, because there's only 2, and it's easier to see these two. This number here, this m, its name is the slope. This number here, this b, its name is the intercept. It's also called the y-intercept. So for all these expressions, the slope is equal to 3 and the y-intercept is equal to 2. We're going to be spending a lot of time talking about why these are useful terms, but it's useful enough for you to be able to recognize right now what the slope and the intercept are. If you have two linear expressions and their slopes are the same and their intercepts are the same, then the same function. So this is a useful enough skill that I want to get a little. I want you to practice it and be good at it. So we're going to work through another example or two. Consider these three. 2y plus 1 is equal to minus 2x minus 1. 3y plus 5 is equal to 6x plus 14. And 3y minus 1 is equal to minus 6x minus 2. Here's the task. Write in slope-intercept form what is the slope, what is the intercept. As I mentioned before, slope-intercept form is all about isolating the variable y and then expanding it completely so that what you have on one side of the equation is just a y and what you have on the other side is a completely expanded linear equation. All right, so why don't you try this? Maybe pause the video, give it a go, and then I'll show you my solutions. All right, you're back. Let's try solving these. So this becomes 2y is equal to minus 2x minus 2, which becomes y is equal to minus 1 times x minus 1. So the slope on this one is minus 1, and the intercept is minus 1. Next one. 3y is equal to 6x plus 9, which becomes y is equal to 2x plus 3. So the slope here is 2, and the intercept is 3. Well, this one's super weird. Y minus 1 is equal to minus 2x minus 2, which becomes y is equal to minus 2x minus 2 plus 1, which becomes minus 2x plus 4 plus 1, which becomes minus 2x plus 5. So the slope is equal to minus 2, and the intercept is equal to 5. I want you to get some practice in on this particular exercise. It's super useful in the long term. So it's really important that you know what we mean by slope-intercept form, and it's really important that you've mastered putting a linear equation in slope-intercept form. Let's move on. Okay. So a brief note, you might be wondering why we call things the slope and why we call things the intercept. So for example, 2x plus 4. We're going to get into this in more detail when we talk about graphing, and hopefully it'll make a lot more sense to you. But the idea behind the slope, that is bad, but the idea behind the slope is that it tells you how y will change if I change x. Incidentally, if you've never seen this notation before, that's the Greek letter delta. Delta is, well, it's the Greek letter delta. Its equivalent is the Roman letter D, and D is the first letter in the word difference, which means change. So anytime we talk about change, you might see this delta. This is probably the first time you've seen it. Delta means the change in, but don't worry about that. The idea here is if I double, if I increase x by one value, so I go from 5 and then I go to x equals 6. Then, so if I change x by 1, then the value of y is going to change by 2 because it's being multiplied by that coefficient there. If I increase the value of x by 3, the value of y was going to go up by 6. Okay? It relates how the value of y changes if we modify the value of x. We're going to talk a lot more about that in detail, but that's why it's called the slope, in essence, because we're talking about straight lines being tilted. Like, honestly, graphically, this number represents how tilty a particular line is. B, on the other hand, is the y-intercept. Its value is just the output value if x is equal to 0. So if you set x equals 0, the value b is just the number, the output, which is kind of obvious when you look at the equation, but it has an important aspect to it when we see it on a graph. Okay, so both these numbers have big important aspects to them graphically, but the overall difference is, like, if we another way to talk about it is b is the number that you start with when x is equal to 0, and then if you increase x by a little bit, this number over front here tells you how much the value of y is going to change. If the number is really big, it means a little bit of change in x is going to cause a great big change in y. If m is a really small number, it means that if you change x by a little bit, m is going to change by an even small number. Okay. Super more on that later. The long and the short of it, though, is that the two numbers we're asking to find, the slope and the intercept, both have consequences in terms of how the function behaves. So, next point. Finding the linear function given 2 points. By this we mean somebody will come up to us and say, hey, when x is equal to 3, f is equal to 7. And when f is equal to 2, x is equal to 8. This information is sufficient for us to figure out an equation of a linear equation, a linear function that satisfies both these terms. But that's not the way things are usually presented to you, and so we're going to neglect that, and instead of talking about pairs of inputs and outputs, we're going to talk about points, which are the same thing graphically. But in this particular game, we'll be giving you 2 points. Let's say 2, 1, and 4, 7. What are these? These are pairs of inputs and outputs. When x is equal to 2, y is equal to 1. When x is equal to 4, y is equal to 7. And the question here is, find our equation that satisfies both of these. So we want to figure out what our 2 numbers are here, so that if I plug in this value of x, you get out this value of y. Same thing for the other one. Does that make sense? Well, long and the story short, we're looking for a value of m and we're looking for a value of b. We're looking for a linear equation, mx plus b, where m and b have actual numbers, where this expression satisfies both of these points. How are we going to do it? It's actually not that hard. For the first point, y is equal to 1 and x is equal to 2, right? And so we want a value of m and a value of b where m times 2 plus b is equal to 1. For the second term, y is equal to 7 and x is equal to 4. And so we're looking for a value of m and a value of b so that m times 4 plus b is equal to 7. Oh, and also our value of m and b have to be the same in both of these. This is an example of a pair of equations that we're asked to solve. solve these equations for m and b. And you should have learned how to do this when you were in high school. It's something fun. There are actually a whole bunch of different methods that we can use to solve them. I'm going to be teaching you a method called isolate and replace, or substitute. So, its steps are pretty simple. Step 1, you're going to take the first equation, that one. That's from the letter I. Okay? You're going to take I, the first one, and you're going to rearrange it, isolating B. One of the variables. We want to figure out what the value B is. So I'm going to rearrange this expression so that B is alone on one side. I'm going to subtract 2m from both sides. 1 minus 2m is equal to B. Step 2, now I'm going to substitute. I'm going to substitute in this equation for the value of B. 7 is equal to m minus times 4. I'm just going to replace the value of B in here with this value here. 1 minus 2m. And then I solve. We solve it for m. Subtract 1 from both sides. Combine those two. Divide 2 by both sides. So m must be equal to 3. And now I'm going to substitute back. In the previous equation, now that I know what m is, I can use that equation to find b. 2 times 3 is equal to b. So you evaluate it, minus 6. So b is equal to minus 5. And you can use these two expressions to put them back in to your function. M is the slope, and B is there. So this equation goes through, both of these points should satisfy this equation. Do you see how that's done? Let's try another example. This is definitely something I want you to be able to do, in part because it involves a lot of different algebraic steps that it's important that you be able to know. Find a line going through 2, 3, and 5 minus 3. So we're looking for mx plus b. We're looking for the values m and b. So point by point, I'm going to plug these values into this expression. So when x is equal to 2, y is equal to 3. Second point. That one. When x is equal to minus 3, y is equal to 5. Whoops, I got that backwards. When x is equal to 5, y is equal to minus 3. And now I have two equations involving two variables that I don't know, and I'm going to combine them to figure out what that variable is. So I'm going to isolate for b. So it's 3 minus 2m is equal to b, and then I'm going to substitute it back into that second equation. 5m plus 3 minus 2m. Going to rearrange. Subtract 3 from both sides. Combine them. Divide both sides by 3. So m must be equal to minus 2, and then I plug that back into the other equation. 3 minus 2 times minus 2 is equal to b. So that's 3 plus 4 is equal to b. So b must be equal to 7. And so my equation must be y is equal to minus 2x plus 7. There's your linear equation. So I'll give you more practice at that in the worksheets. There's one last topic we need to cover, which is the x-intercept. I've already told you how to find the y-intercept. You just expand the function, you just expand your expression out until it's in point-slope form, and the y-intercept's that last number. All right, hold on. I'm going to take a slight run at this. We'll talk about the y-intercept again. It's the value of y when the value of x is equal to 0. So for any linear equation, there'll be a number called the y-intercept, and all you need to do to find it is set x equals 0. X-intercept. Similarly, there's going to be a value called the x-intercept. It is the value of x when y is equal to 0. This is actually trickier to find than you might think, because if you think about it, y is the output of an expression. So what we're looking for is the root. By x-intercept, we're talking about the root of the linear function. So if somebody gives me an expression, here's a linear function, x plus 8, and they ask me for the x-intercept, how do I figure out its value? We already talked about how to find roots. You set y to equal 0. Then you rearrange. You're solving for x. Divide both sides by 4. So x equals 2 is the x-intercept. That's a skill we've already talked about doing. I presume that you've actually gotten pretty good at it. Essentially, it's just the root of the linear equation, but we call that value the x-intercept. The reason for all these different names when it comes to linear polynomials is that they all have applications in graphing. What we mean by x-intercept, what we mean by y-intercept, what we mean by slope, they all make a lot more sense when you can see a graph. Okay, so to review, here's our medicine wheel. A linear function is described as a relationship between two variables, x and y. They don't have to be x, they don't have to be y, but one of them is the independent variable, and the other is the dependent variable. So maybe instead of the letter y and the letter x, maybe you're measuring plants, or measuring the height of plants, h, and you're controlling the amount of moisture, m. In that case, the independent variable would be m, that's the thing you're changing, and the thing you're measuring, the thing that depends on the other thing, the height, h, right? But in a linear equation, there's an independent and a dependent, and then there are two numbers. When you write it out in points form, there are two important numbers for defining it. There's the slope, m, and there's the y-intercept, b. Okay. If somebody tells you the slope and the y-intercept, you can it's really easy to write one of these linear functions out. Somebody just says, hey, the slope is 2, the y-intercept's 4. You just plug those into the general form, and that tells you the linear equation. So in other words, any specific linear equation is defined in terms of what its slope and what its y-intercept are. Those two numbers are what define a particular linear function. So if somebody gives you those two numbers, you're good. All right, that's it for this particular lesson. Have a nice day.